Because a square root is not considered to be in simplest form if it has any perfect square factors, we need to be able to tell whether a variable expression is a perfect square. Here's how we can do it. Let's take, for instance, the expression x squared. To tell if x squared is a perfect square, we need to know if we can take the square root of x squared and get a variable expression with an integer exponent. Let's see if the square root of x squared gives us an integer exponent. In general, to tell whether or not this works, we want to rewrite the square root as an exponent. So we're going to take the number or the expression inside the square root, which is x squared. And then we're going to apply the rule that tells us that the square root of a number is the same as raising that number to the 1/2 power. Then we apply the rule of exponents that states, when raising a power to a power, multiply the powers. This tells me that x squared to the 1/2 power is going to be found by taking x and raising it to the 2 times 1/2 power. 2 times 1/2 is 1. So this is the same as x to the first power, which is just x. This answers the question as to whether or not x squared is a perfect square. Since when we took the square root of x squared, we got a variable with an integer exponent, no fractions in the exponent, x squared is a perfect square. Now let's consider x to the 5th. Is x to the 5th power a perfect square? Well, here's what we need to do. We need to see if we can take the square root of x to the 5th power and get an integer exponent. Again, we will apply the rule that states the square root is the same as raising an expression to the 1/2 power. So let's take the expression inside the square root, that's x to the 5th, and then raise it to the 1/2 power. Again, I will use the rule that states when raising a power to a power, multiply the powers. 5 times 1/2. Well, 5 times 1/2 would look like this. 5 times 1/2. I'm multiplying fractions. I can write anything as a fraction by putting it over 1, and now I multiply straight across. Numerator times numerator, 5 times 1 gives me 5. Denominator times denominator, 1 times 2 gives me 2. And I can't simplify this. So this gives me x to the 5/2 power. Notice that my exponent is not an integer. It's a fraction that can't be written as an integer. So x to the 5th power is not a perfect square. Let's explore some other possibilities. Let's consider x to the 6th power. Is x to the 6th power a perfect square? To find out, we need to take the square root of x to the 6th power. Again, we will use the rule that states the square root of an expression is the same thing as taking that expression and raising it to the 1/2 power. X to the 6th power to the 1/2 power. Here I'm raising a power to a power, so I multiply the powers. 6 times 1/2 is 3. Since I end up with an integer exponent, x to the 6th is a perfect square. In general, a variable expression will be a perfect square if the exponent is even. Effectively, this means that when I take the square root, I'm raising it to the 1/2 power. What I'm doing is dividing 6, or the exponent of x, by 2 every single time. If 2 goes into the exponent, it'll be a perfect square. In the example with x to the 5th, 2 does not go into 5. That's why we were still left with a fractional exponent, and x to the 5th is not a perfect square. This idea can be generalized into any nth root. If, for instance, we want to consider whether x to the sixth is a perfect cube, is x to the sixth a perfect cube? X to the sixth will be a perfect cube if I can take the cube root of x to the sixth and get an exponent that is an integer. Well, the cube root of x to the sixth tells me to take whatever expression is inside the radical, in this case, x to the sixth, and raise it now to the 1/3 power. This is x to the sixth to the 1/3 power. I'm raising a power to a power, so I multiply the powers. 6 times 1/3. I can cancel factors. 3 goes into itself once and into 6 twice, leaving me with 2/1. So 6 times 1/3 is 2, so this is x squared. Since the cube root of x to the sixth is x squared and my exponent is an integer, x to the sixth power is a perfect cube. Let's try another one. Let's try x to the 10th power. Is x to the 10th power a perfect cube? If it is, I will be able to take the cube root of x to the 10th power and get an expression that has an integer exponent. Again, I will use the definition of a cube root that tells me that I can take an expression that's inside of a cube root, in this case x to the 10th, and raise it to the 1/3 power. When raising a power to a power, multiply the powers, so I'll need to take the power 10 times the power 1/3. Write everything as a fraction by putting it over 1, and then multiply straight across. I cannot simplify 10/3, so this means that the only way to write this with an exponent is x to the 10/3 power. 10/3 is not an integer. Therefore, x to the 10th power is not a perfect cube. Let's take a look at what's going on here. To find out if it's a perfect cube, effectively what I'm doing is raising the expression to the 1/3 power, which means what I'll be doing is taking the exponent, 10, and dividing it by the root, in this case the third root or the cube root. If 3 goes into 10, then x to the 10th power will be a perfect cube. Since 3 does not go into 10, x to the 10th power is not a perfect cube. Looking at this, again we're finding perfect cubes. 3 does go into this exponent of 6. Therefore, x to the 6th was a perfect cube. Now if you don't quite understand that piece, you can always go back to this definition right here, that the cube root is the same as raising to the 1/3 power and seeing if you get an integer exponent. You can apply this to any nth root that you would like to find. You can find perfect 4th powers of variable expressions and perfect 5th powers. Any power that you'd like to find, you can do using this method.